So for this recording, I will be walking through the steps for doing a multiple regression analysis. The basic steps for the analysis are kind of in a three-stage model. So if you think about multiple regression as doing 3 steps, and within those steps there's multiple steps, then you're in good shape. So the first thing, of course, is to check all your assumptions, fix them if needed. If you have outliers, multivariate outliers, to kick them out. If you have problems with normality, to do transformations. So get all of your assumptions set. Second is to look at your overall model when you run your regression. You want to look at your R value, your R square, your B, beta, and your regression ANOVA out of all of the data that you have to kind of get a sense of what's the strength of association that you can see in the R square and the beta weights, and then what is your data significantly different than random data, which would be your regression ANOVA. And then you want to go in and look at all of your individual predictors. So now we're looking at beta weights, particularly B and beta, the t-tests for each of those betas, how significant the t-test is, and something called partial and then sometimes semi-partial correlations, which will tell you how much variance each variable can predict on its own of the outcome variable. So those are the 3 steps: assumptions, overall model, and then each individual coefficient. So I want to give you an example here of a multiple regression that could work for kind of going step by step. And the first step, of course, is to look at the assumptions and the overall regression and then each individual. And we're going to spend most of our time on each individual predictor because that's where the details are. But let's say you have a study where you're trying to look at agreeableness that people rate on themselves and their religious commitment, and to see if they can predict their God image or whether they see God as agreeable. But agreeableness, self-rating, and religious commitment may predict each other. And in fact, if they have really high prediction, with each other, then you could have a problem with multicollinearity and all kinds of interesting things. So you're always asking, just like in the conceptual map about the conceptual information I shared about the sponges going into the bucket, how much does agreeableness do on its own? How much does religious commitment predict on its own, and how much does the overlapping variance of the 2 of those together predict the dependent variable of God image as agreeableness? And so your R squared is going to tell you all the sponges thrown in together, all of these 2 predictors and their overlapping variance together, how much of the bucket, what percentage of variance of the bucket of water, in this case the bucket of variance of God image, can be predicted by these predictors. And what's left is anything else that can predict God image, right? Anything, whatever we don't cover. So say together they are able to predict 40% of the variance of God image. That means 60% of the variance is predicted by something else in the world, right? Error, other variables we didn't measure, all of that. Right. So that's kind of like the big picture. That's the main R square. And then the ANOVA that goes with the R square that you're going to examine is just telling you whether that altogether, all of them, is significantly different than random data, right? If they can predict the outcome better than random data. Before we go on to talk about individual predictors as we're going through step by step, I do want to stop for just a second and talk about residuals and regressions, because the word residual is used quite a bit in the regression family of equations and analyses. And if you don't understand the concept, I want to make sure it's really clear for you. So a residual is the difference between a predicted score and an actual observed variable. So if you have your line, so you remember you have your regression line, right? That looks like this. Then you had all your dots that go around your regression line. The residual would be the distance between the line and each dot. So each dot, each point of data, each individual person would have not only their X value, their Y value, right, of what they got, but they would also have a residual value for each person. That is, how far is my dot on this, field of data from the line, right? How far am I? Am I someone that's very far from the line, or the regression line, or am I somebody that's right on the line and my residual is practically 0? So everybody gets a residual value in addition to an X value and a Y value. Your textbook in Grimm and Yarnall that I have as a reading in this course on page 37 has some really nice information. I think it's a good explanation of residual. It's a little bit better actually even than your Mertler textbook. Okay, moving on to the next step. We are now done with looking at the R-squared and looking at the regression ANOVA overall, and we want to look at each individual predictor, whether you have 2 or 3, however many you have. So B is the amount that the Y variable, the outcome variable, changes when you change the X predictor by 1 unit, okay? So B is a raw score. It's not weighted, meaning you can't compare the B's to each other because they're all based on the actual measurement that is used, right, for the study. But it's useful information, and in fact, in the APA manual for presenting results for regression, you include the B value for each predictor as part of your results that you present. However, because people wanted to be able to compare things to each other, they created something called a standardized version of B, which is called beta, or sometimes called beta weight. And this beta weight equals the correlation where there is a single predictor, meaning if there are 2 or more predictors, beta weights can be compared to each other, and you can see which one's stronger and which one's weaker, and you can even rank them. In fact, when I'm presenting results of a regression, I will typically present each of the predictors in order by beta weight. So the strongest one first, and then going down to the weakest one, depending on how many I have. If there are 2 or more, beta weights can actually be larger than plus or minus 1, so don't let that throw you. That has to do with how the standardization occurs. So as you're looking at the results here in this step of looking at the individual predictors, we're in kind of step 3 of regression. As you're looking at it, you're going to get a lot of different data. So it's not like other statistics you might have done in the past where really all you get is like an F value and a P value, and that's it. You're going to have a beta weight, a raw B, a T test, a P value for the T test, a correlation, a partial correlation, a semi-partial correlation for each of them. And all of those things tell you a little bit different bit of information. And we're going to be walking through all of that. Okay, so the T ratio and its associated p-value is telling you whether you'd like to take this variable into account when you're making a prediction, whether you'd like to know the value of this variable for an individual. And it's going to tell you whether that predictor variable, so it's going to be in a line of data, it's going to tell you whether that predictor variable is significantly different than random. So similar to the regression ANOVA, which compares your data to random, the T ratio compares your data also to random data and tells you whether or not it's a significant predictor compared to random. The beta weight, when compared to other beta weights of an explanatory variable, tells you how important the variable is in helping to explain why the dependent variable takes varying values across the sample. So I do want to point out here a couple things. The T ratio is based on the individual, right? So it's kind of an examination at that level. The beta weight is using your sample, right? And so it's taking it at the sample on the theoretical level. And the B, the raw B, is a population estimate of the unstandardized coefficient. It's the slope or ratio of rise to run on the regression line. But note how that's the population. And if you remember in all statistics and research design, population is this theoretical thing you can never get your hands on, right? I know that you're looking at it going, but that's based on our sample. But just understand that how they're working this is they're saying B is population. Beta weight is something that we've standardized, and so that becomes part of your sample. And the T ratio is looking at the value at the individual level, right? Whether on an individual, would you want to know whether it's significantly different than random? So sometimes that's helpful for people. Sometimes this is a little confusing. Hang in there. Okay, so where did this beta weight formula come from? Now, this is one of those things that it's not necessary to really understand the beta weight formula to be able to run SPSS and then interpret what SPSS has to say and write it up in a results section and understand your data basically. But on a little deeper level, you can use your understanding of the beta weight formula to understand like what is it that I'm actually looking at. So the beta weight is calculated with the B value times standard deviation of X over the standard deviation of Y. Or you can switch these two, right, obviously, right, and you can just be the same thing. The B equals the beta over standard deviation of Y divided by standard deviation of X, sorry. So there's multiple prediction variables. So in actuality, it's the beta weight for one of them, and then you see it going through this. So R stands for the correlation coefficient of the first variable minus the second, and then the overlapping correlation of the first and the second. So that's that overlapping areas of the sponge showing up there. And then the same thing happens in the denominator. The overlapping area of the sponge is subtracted from 1, and 1 would be everything, right? So this is the difference between all of it being predicted and then what we are able to predict with the overlapping variance right here. So some people look at this and they go, oh, that makes perfect sense. And they just think like a math brain, right? And some of you are going like, oh yeah, that's really helpful. Thanks for sharing that, Dr. Jen. And some of you are saying right now, this is just Greek to me. Like, why are you showing me betas and R's and 1s and 2s? And I don't get this. And that's okay. I am not going to quiz you on this in my class. But for those of you who find this helpful to kind of take it to a deeper level, that's great, kind of an enrichment level. But if this is something that confuses you, don't worry about it. Just understand that it has to do with the variance. The beta weight is created from the raw data, and then the variance, because standard deviation is a variance measure of your X and Y variables. Here I have a picture of what this looks like as we're talking through the predictors. This is what SPSS is going to end up giving you, and you can look in your Mertler textbook for this a little bit more. But what you have here are 4 predictor variables, and you can see that the dependent or outcome variable is the science score, and the predictor variables are math score, female, social studies score, and reading score, right? And you can see that you've got the raw B score right there, right? You can see those. You've got some standard error, and your textbook talks a little bit more about that. That's information about how much residual you have or how much error you have for each of them. But it's not standardized, right? It's not as standardized as you would like. So the standardized coefficient on beta will tell you right there which ones are the best predictors. So if you look and see math score of 0.36 is the highest beta, that's your best predictor of science score, followed by reading score, which is 0.347. And then the next one down is gender, which is a negative 0.101. And it looks like they dummy coded that. Since gender is categorical, so you can't do a regression with gender, what you can do is say female or not, and code it that way. So it's a very small continuum from 0 to 1. And so that's there, but it's only a negative 0.10. That's fairly small. And then social studies score of a 0.054 is getting awfully close to 0, right? And you can see that reflected in your t values as the next, right? So if you look at the significance levels for the t values, you do have significance for math and for reading. They're both p less than 0.05. Female gender is right at this 0.051. So it's just not, just barely not significant. And I know you're not supposed to talk about it that way. It's supposed to be either or. But we all know that there's kind of a magnitude of influence here. But then social studies score is definitely not significant, right? So there's nothing there. And then you've got these confidence intervals as well for your B as to what your B would be given, an X score of 1 kind of thing, that what your B would be. So those are really nice to kind of get you a sense of like, oh, we've got all this information coming in for B, for beta, for T, and we can kind of group it, categorize it as significant or not. And remember, still, significance isn't the most important thing because we're in regression land. The beta weight would be the most important data or information on this screen that you're looking at here. Okay, so back to talking about the big challenge with multiple regression as we walk step by step through the process. When you have 2 predictor variables, you actually have 3 contributions to the outcome, as we've talked about. You have IV number 1, you have IV number 2, right? Predictor 1 and 2. And then you have the overlapping variance of IV 1 and 2, and you can see that in this picture here. IV1, IV2, and then this is their overlapping variance. And this would show you how much they can predict of the outcome variable in this Venn diagram that we're looking at here. So the question we always ask is, what are we going to do about that problem of this overlapping variance? What's predicting this? So one of the ways that we handle that problem of overlapping variance is to look at something called the various many types of correlations, right? There's actually multiple kinds of correlations. There's the Pearsons correlation, which you already know, and sometimes in SPSS output, this is called the zero order correlation. So just be aware that those are the same thing. Then there's these kind of funky correlations called partial and semi-partial correlations. And this is additional data you can get on each of your individual predictors and how well they predict the outcome variable. And these will tell us how that overlapping variance has been handled. So let's start with the easy one. Pearson zero order correlation. This is just a relationship between the predictor and the outcome variable, a measure of linear association. This is assuming all other variables don't exist, essentially, right? There's no other variable being taken into account here. It's just as though you're looking at a universe of two variables, right? Two continuous variables, your predictor and your outcome, and you can look at those, and that's useful information, but overlapping variances are being ignored in this way of doing correlations. You can also get output on something called partial correlation. And a partial correlation, what it does is it removes the variance from the other variables, and then it tells you how well that one predictor or independent variable can predict the outcome. You can do it for either one of these, but it would be the correlation of, it's just for IV1, it would be just looking at this section alone. A partial correlation would look only at section A. It's important in multiple regression because we have this B section and we never really know how big it is, right, until we kind of parse it all out. You can calculate this all on its own by clicking Analyze Correlate Partial within SPSS, and you can also click an option within multiple regression that will give you all your part and partial correlations, and then it'll be part of the output there. So you can kind of look at it and see, okay, this whole thing, A and B together, would be my Pearson or zero order correlation, and this section right here would be my partial correlation. Okay. So I'm going to give you 4 different definitions of partial correlation because a lot of students struggle with this concept, and so I've pulled this from 4 different sources, and I think it's helpful sometimes to get different definitions and you can kind of see it all come together. So one definition is the correlation that remains between two variables after removing the correlation that is due to their mutual association with other variables. It's only if there's more than one independent variable. A second definition, the correlation between the dependent variable and an independent variable when the linear effects of the other independent variables in the model have been removed from both. Third, the partial correlation procedure computes partial correlation coefficients that describe the linear relationship between two variables while controlling for the effects of one or more additional variables. This is from the help topics in SPSS, which is sometimes actually helpful. And then a fourth definition is if one independent variable only, the regular zero order correlation and the partial correlation would be the same number because there's nothing to partial out if you only have one independent variable. So statisticians were pretty excited about having the partial correlation versus the Pearson correlation to be able to look at A and the C in that picture. However, there's one more way to partial things out that people thought, maybe we should do something a little more strict, a little more conservative. And this thing is called the semi-partial correlation squared. This semi-partial correlation squared, which is denoted here as an SR squared, that is considered the more useful measure out of all of these break it apart into little pieces measures that we're doing here in this final step of running a regression. The semi-partial correlation squared tells us the unique contribution of the IV to the total variance of the DV compared to. So it's a ratio. In semi-partial correlation, the contribution of other independent variables is taken out of only the independent variable that you are examining, not of the denominator, which would be the whole dependent variable. In contrast, the partial correlation takes the contribution of the independent variable taken out for both the independent and the dependent variable, so both the numerator and the denominator in the calculation. Your Tabachnik text, now whether you have a current version or not, is around page 140. Mertler and Vanetta look around page 176. I'm always cautious about this because we could get changes based on different versions. And SPSS output, you can take what's called the part correlation and output. So what you're going to get an output for semi-partial correlation, it's going to be just called part, P-A-R-T, right? And the one next to it's going to be called partial. And this one's going to be called part, and then you actually have to pull your calculator out and square it. And then you can report your semi-partial correlation. It's going to be small. It's always really small. But we get really excited about really small numbers here because we have basically taken out all other contributions, and we're still comparing it to everything that can be predicted in the dependent variable. So it's a very conservative measure of prediction. So I'm going to walk us through some pictures here and the formulas, and I'm hoping this is going to help everybody kind of solidify the concepts. This is a standard multiple regression picture that we're looking at here with two predictors. One predictor here, second predictor there. Here's our outcome variable up here, right? We've got a squared correlation would just be comparing A to B, right? How big is A to B? The numerator, and then the dependent variable would be A, B, C, and D, right? And that would tell us our correlation. What is the percentage of A and B compared to D, which is 100% of the outcome, right? Independent variable 2, in contrast, would be C and B, right? Compared to A, B, C, and D, which is 100% of the outcome, right? You get that percentage. But of course, if you're doing IV1, IV2, and you're presenting both, you're using B twice here, which is why the standard correlation, squared correlation, is not ideal. But it's information. Okay, what we're looking at here is a squared partial correlation. And for this, what you're comparing is just A. So we're leaving out B and any shared variance, just the contribution of A to A and D, right? So it's not 100% of the outcome, but because we've already, in this process, we've removed everything associated with IV2 from both the numerator, right, and from the denominator, and that will give us our partial correlation. And then similarly for IV2, we're looking at what percentage is C for comparing to C and D together. So again, in the denominator, it's not 100% of the outcome, it's the outcome after taking the effects of IV1 out of it. And so this is the picture of a squared semi-partial correlation. How is that one calculated? This one's taking just this little piece here, the unique contribution of independent variable 1 after removing the shared. So the shared is not part of it, okay? But it's comparing it in the denominator to 100% of the outcome, right? We have not removed this part out like we did in the partial. This was why it's called a semi-partial. And then the same thing for IV2. It's just this little part of C right here, right? The unique variance predicted compared to 100% of the outcome. And that's why it's considered the best, is because we get to keep all of the outcome in the denominator. But we just know, like, okay, well, we have lost the shared variance, right? And so we're only looking at unique variance now. Okay, this is just a summary. You might do this as part of a group if you're studying, and we probably in my class will do this a little bit in class as a group time to describe the difference between a partial and a semi-partial correlation, to be able to do that on a Venn diagram, to be able to do that descriptively, and then to be able to do that with the ABCD formulas. And then also to be able to talk about what the steps are for doing a standard regression, step by step by step. You can use your textbook a little bit on figure 7.27 to help you with that. But some of the partial and semi-partial stuff is not in there. We will be covering how to do that in our SPSS lab in class. We have not covered hierarchical regression in this video, but I do plan to cover it a little bit in class because sometimes people do need to do a hierarchical regression in our program for their dissertation, and I wanted you to be prepared for that. So I hope that this has been helpful to you. Thanks.